Hello everyone, good evening. So here we shall solve some KCET previous year questions on the chapter wave optics. So any doubts if you have in any steps of the solutions, then please write us in the comments section. We shall clarify them in the subsequent videos. And in any other chapter of physics, if you feel more difficulty, then also please mention the name of that chapter in the comments section. Also, some important homework questions will be uploaded in the Sapience Education application on every chapter, which are based on the previous year KCET exam. So please install our Sapience Education application, whose link has been provided in the description. So here we shall start from the very first question onwards. So it is told that in Young's double slit experiment, third slit is made in between the double slits. Then what will happen? Then the contrast in between the bright and the dark fringes is reduced. So option B is the correct answer. In a Fraunhofer diffraction experiment at a single slit using a light of wavelength 400 nanometer, the first minimum is formed at an angle of 30 degrees. The direction theta of the first secondary maximum is given by. So for Fraunhofer diffraction in a single slit, we have for the nth secondary maxima, the angle theta is given as sine theta equals to 2n plus 1 lambda by 2a. The first and for first minima we have that sine theta that is equal to lambda by a. So here for the first minima the angle theta is given as 30 degrees. So therefore sine 30 degrees that is equals to lambda by a, so which is equal to half. So lambda is equal to a by 2. Now therefore we have to find the angle theta for the first secondary maximum. So here n is equal to 1 in this formula. So therefore sine theta that will be equal to 2 plus 1 into lambda is a by 2 divided by 2. So a and a will cancel. So this is equal to 3 by 4. So theta will be equal to sine inverse of 3 by 4. So at this angle, the first secondary maximum will be formed. So option D is the correct answer. Then in question number 3 it is told an unpolarized beam of intensity I0 falls on a Polaroid. An unpolarized beam of intensity I0 falls on a Polaroid. Unpolarized beam of intensity I0. The intensity of the emergent beam is how much? Intensity will be I0 by 2. Since after crossing the Polaroid, the unpolarized light will be polarized. Along the path axis. So option C is the correct answer. Then in question number 4 it is told two sources are said to be coherent if they produce waves, if they produce waves having a constant phase difference, their phase difference delta phi, that should be independent of time, should not be a function of t, should be independent of time. So it should be constant in time. The phase difference is always constant. So option A is the correct answer. For the constructive interference, the path difference in between the two interfering waves must be equal to. So we know that the phase difference delta phi, that is equal to k delta x, where delta x is called the path difference and delta phi is called the phase difference, and k delta x, that should be equal to 2n pi. Then only there is constructive interference. So therefore k is 2 pi by lambda into delta x, that should be equal to 2n pi. So 2 pi will cancel, so delta x should be equal to 2n pi, 2n lambda. Sorry, delta x should be equal to n lambda. So when path difference is equal to an integral multiple of the wavelength, then only there is constructive interference. So option C is the correct answer. So in the next question, it is told two luminous point sources separated by a certain distance are at 10 km from an observer. Two luminous point sources separated by a certain distance are at 10 km from an observer. So two luminous sources are separated by a distance of 10 km from an observer. 10 km from an observer. Okay. If the aperture of his eye is 2.5 into 10 power minus 3 meter and the wavelength of the light used, that is 500 nanometer, the distance of separation in between the two point sources just seems to be resolved. That is how much. So we know that, so according to the Rayleigh criterion, the angular separation in between the two point sources, that should be equal to 1.22 lambda by dE. 1.22 lambda by dE, where dE is the aperture of his eye and lambda is the wavelength used, and this theta, that should be equal to A by D, where this D is the distance of these two point sources from the eye of the observer. So this D, so D is equal to 10 km, and this A we have to find. A is the distance of separation in between the two point sources. So therefore A will be equal to 1.22 lambda by dE into D. So this will be equal to 1.22 into lambda, that is 500 nanometers into 10 power minus 9, into D, that is 10 into 10 power 3, since 10 kilometer it is, divided by dE. D is 2.5 into 10 power minus 3. So this much meter. So 2.5, so 4 is 10, then 4 5 are 20. So this is 1.22 into 2 into 10 power 3 into 10 power 3 to 10 power minus 9 divided by 10 power minus 3 is also there. This much meter. So this 2, 3 will cancel out. 10 power 9, 3 plus 3 plus 3, that is 9. So it is 2.44 meter. So option C is the correct answer. Then question number 7, it is told Young's double slit experiment gives interference fringes of width 0.33 millimeter. Young's double slit experiment gives interference fringes, so the fringe width beta. So if beta is the fringe width, that is equal to lambda d by d, that is equal to 0.3 millimeter. So it is 3 into 10 power minus 4 meter. A thin glass plate made of material of refractive index 1.5 is kept in the path of light from one of the slits. Its refractive index n is 1.5. Then the fringe width becomes so when this glass plate is placed, so then what happens, on all the fringes will get shifted, by a length y naught is equal to d by d, where small d is the width, the separation of the two slits, and d is the distance in between plane of the slits and the screen, d by d into n minus 1 into t, where t is the thickness of this glass plate and n is the refractive index. So by this much, all the fringes will get shifted, but the fringe width will not change. The fringe width will remain unchanged. So the fringe width will remain as 0.3 millimeter only. So option B is the correct answer. And question number 8 is told red light of wavelength, the wavelength of the red light, that is equal to 625 nanometer. It is incident normally on an optical diffraction grating. Red light is incident normally on an optical diffraction grating. Diffraction grating is there. Diffraction grating. Wavelength is 625 nanometer. Optical diffraction grating with 2 into 10 power 5 lines per meter, including central principal maxima. How many maxima may be observed on a screen? It is far from the grating. The red light of this much wavelength is incident. Diffraction including central principal maxima. How many maxima will be observed on the screen which is far from the grating? So n is, if n is the number of lines per meter, which is 2 into 10 power 5, and so then for the nth order maxima on the screen, the angle theta is given as sine theta equal to n lambda by n. And this theta is called the angle of diffraction. And so therefore the maximum value of screen far from the grating, the maximum value of sine theta is 1. So I can say that n lambda by n, that is equal to 1. N lambda by n, that is equal to 1. Sorry, sine theta by n, that is equal to n lambda. There is something wrong. Here sine theta by n, that is equal to n lambda. So I can say that sine theta will be equal to n into n into lambda. So n into lambda, that is equal to 1. So the number of maxima that we found, that is 1 by n lambda. So these many maximas will be formed from the central maxima on either sides, excluding the central maxima. So it means here also n number of maxima, here also n number of maxima will be formed, excluding the central one. So therefore, including central maxima, the number of maxima formed on the screen, including the central maxima, the total number of maxima that is formed on the screen, that will be equal to 2 into n plus 1. So therefore the answer will be 2 by n into lambda plus 1, that we have to find. And here lambda is this, which is 625 into 10 power minus 9 meter. So therefore the answer will be 2 by n lambda plus 1, so that will be equal to the number of maxima which is formed. So 2 by 2 into 10 power 5 into 625 into 10 power minus 9 plus 1. So this will be 2 and 2 will cancel. So this is 10 power minus 4. This is, so this I can write 100 into 100 is 10 power 4. By 625 I can write 25 into 25 plus 1. So 25 4 is 100, 25 4 is 100. So this is 16 plus 1, which is equal to 17. So 17 maximas are formed, including the central maxima. So option B is the correct answer. Then in question number 9, it is told the wavelength of the light used in Young's double slit experiment is lambda. The intensity at a point on the screen where the path difference is lambda by 6 is I. If I naught denotes the maximum intensity, then the ratio of I and I naught is how much? So the resultant intensity at any point that is given as I resultant, that is equals to uh, 2 I naught 2 I naught plus 2 I naught into 1 plus cos delta phi. So phi is the phase difference. So when the path difference delta x is lambda by 6, then the phase difference, that will be equal to k delta x, where k is the angular wave number, which is 2 pi by lambda into lambda by 6. So that will be equal to pi by 3, and cos pi by 3, that will be equal to half. So therefore the resultant intensity I in that case on the screen, it will be 2 I naught. I naught is the maximum intensity. So sorry, here I naught, if it is the maximum intensity, so then, and I1 is suppose the intensity of from one of the slits, so then I can say that when cos delta phi is 1, then we have maximum intensity. So that will be 4I1. So 4I1 is I naught. So this is 2I1 into 1 plus half. So I1 is I naught by 4. So it is 2 I naught means I naught by 2. So this I can also write I naught by 2 into 1 plus cos delta phi. So I naught by 2 into 3 by 2. It is 3 I naught by 4. So therefore the ratio of I and I naught, that is equal to 3 by 4, which is equal to 0.75. So option D is the correct answer. Then in question number 10, it's told that what is the minimum thickness of a thin film required for constructive interference in the reflected light from it. Given the refractive index of the film, that is n, that is suppose 1.5, wavelength of the light incident on the film, that is 600 nanometer, which is 600 into 10 power minus 9 meter. What is the minimum thickness of a film that is required for constructive interference in the reflected light from it? Minimum, okay. Constructive interference in the reflected light. So it will be like this form. It means that 2 times n into the thickness, that should be equal to n plus half into lambda, where 2 mu into t, let the refractive index be mu, it will be 2 mu t equal to n plus half into lambda for n, where n is the nth order maximum. Nth is the order of maximum. Okay. So for minimum thickness, where t is the minimum thickness, for minimum thickness t, n should be equal to 0. Therefore, you should have 2 mu into t, that should be equal to lambda by 2. Therefore, t should be equal to lambda by 4 mu. So that should be equal. That will be equal to the minimum thickness the minimum thickness, that would be equal to the wavelength that is used, which is 6 into 10 power minus 7 meter. I can write this as 6 into 10 power minus 7 meter divided by 4 mu, 4 into 1.5. So 15 4 is 60. That will be 10 power minus 5, minus 7 meter, or I can say it as 100 nanometer. So option A is the correct answer. Then in question number 11, it is told the critical angle for certain medium is sine inverse 0.6. The polarizing angle of that medium is the polarizing angle. So the critical angle, if it is C, then we have sine C, that is equal to 1 by n. Means the critical angle C is given as sine inverse of 1 by n, where n is the refractive index of that medium. Now according to the Brewster's law, we have that n, the refractive index n is equal to tan into IP, where IP is called as the polarizing angle. IP is called the polarizing angle. So now therefore here 1 by n, that is equal to 0.6, which is 3 by 5. So n is equal to 5 by 3. So therefore 5 by 3, that should be equal to tan into IP. So therefore the polarizing angle should be tan inverse of 5 by 3, which is equal to tan inverse of 1. It is 1.66667. So option C is the correct answer. In question number 12, it is told wavefront is the locus of all points where the particles of the medium vibrate with the same phase. Should be phase. Vibrate with the same phase. So option A is the correct answer. Question number 13 is told two monochromatic light waves of amplitudes 3a and 2a are interfering at a point. They have amplitudes 3a and 2a. They are interfering at a point having a phase difference of 60 degrees. Then the intensity at the point will be proportional to. Now the resultant amplitude means the resultant intensity is proportional to the square of the resultant amplitude. Now the resultant amplitude, square of the resultant amplitude will be equal to the square root of a1 square plus a2 square plus 2a1 a2 cos delta phi. Since we have to consider them as phasors, we have to consider them as, it means we have to do the vector addition of the two amplitudes to get the resultant amplitude. Suppose this is amplitude A1, this is amplitude A2, and their phase difference is delta phi. Then we have to find the resultant amplitudes by doing their vector addition. We have to find the resultant amplitude by doing vector addition. So now therefore the square of the resultant amplitude, that will be equal to A1 square plus A2 square plus 2A1 A2 cos delta phi. Now therefore here A1 is 3a, A2 is 2a. So therefore I can write 3a whole square plus 2a whole square plus 2 into 3a into 2a into cos 60 degree. Cos 60 degree is half. So this is 9a square plus 4a square plus 2 into this is half. This will cancel to 6a square. So this is 6 plus 4, 10 plus this is 19a square. So therefore the resultant amplitude is proportional to 19a square. Also option D is the correct answer. Then in question number 19, it is told consider the following statements in case of Young's double slit experiment. A slit S is necessary if we use an ordinary extended source of light. Consider the following statements in case of Young's double slit experiment. A slit S is necessary if we use an ordinary extended source of light. A slit S is not needed if we use an ordinary but well collimated beam of light. A slit S is not needed if we use a spatially coherent source of light. So all those statements are correct options. Since a slit in a double slit experiment, the slit is necessary if we use an extended source of light. Slit is not required if we use an ordinary but well collimated beam of light. Collimated means that the beam should be considered to be a parallel beam. Parallel beam should be there. Slit S is not required if we use a spatially coherent source of it. Spatially coherent, it means that their phase difference is independent of time. Phase difference is independent of time. This is called spatially coherent source. Okay. So 1, 2, and 3, all the statements are correct. Then in question number 15, it is told that a parallel beam of light of wavelength, that is a parallel beam of light rays, it is having a wavelength 6,000 angstrom, which is 6,000 into 10 power minus 10 meter. It is diffracted by a single slit of width, A, that is 0.3 millimeter. The angular position of the first minima of diffracted light is. So the angular for the first minima we should have, sine theta, that is equals to lambda by A. Sine theta, that is equals to lambda by A, where A is the width of the slit, lambda is the wavelength used, and theta is called the angle of diffraction. Angular position of the first minima. So sine theta, that will be equal to 6 into 10 power minus 7, I can write, divided by A, that is 3 into 10 power minus 4. So this will be 3 to the 6, so this will be 2 by 10 power 3. So this is 2 into 10 power minus 3. This much value. So therefore sine theta is very small. So theta is also approximately equal to sine theta, since sine theta is very small. Since sine theta is very small. So therefore the angle theta also should be approximately 2 into 10 power minus 3 radian. Option A is the correct answer. And in question number 16, it is told the critical angle of a certain medium is sine inverse of 3 by 5. This is the critical angle, which is also equal to sine inverse of 1 by n, where n is the refractive index of that medium. Then the polarizing angle of that medium is. So therefore, according to the Brewster's law of polarization, according to the Brewster's law of polarization, we have, that is Newton's law of polarization, we have that polarizing angle of the medium Newton's law of polarization. Yeah, we have that tan IP, that is equal to n, where n is the refractive index of the medium. Therefore, here the n that will be equal to 5 by 3. So therefore, IP polarizing angle that is equal to tan inverse of 5 by 3. So option B is the correct answer. Then in question number 17, it is told, in Young's double slit experiment, fringes of width beta are produced on the screen. In Young's double slit experiment, fringes of width beta are produced on the screen, kept at a distance of 1 meter from the slit. So from the slit, the screen is placed at a distance of 1 meter. The screen is placed. So D is equal to 1 meter here. When the screen is moved away by 5 into 10 power minus 2 meter, the fringe width changes by 3 into 10 power minus 5 meter. The separation between the slits is this. The separation in between the slits D, that is equal to 10 power minus 3 meter. The wavelength of the light used in nanometer is. So how much is the wavelength of the light? So we know that the fringe width beta, that is equal to lambda d by d. So now therefore, when this d will change, the beta will also change. So therefore I can say that delta beta, that is equal to lambda delta d by d. Since lambda and d, these two are fixed, they are not changing. Only this distance d is changing. So the fringe width beta is also changing. So therefore, change in the fringe width, that is equal to 3 into 10 power minus 5, that is equals to the lambda into change in the d, that is 5 into 10 power minus 2 divided by d is 10 power minus 3. So therefore, lambda that will be equal to 3 into 10 power minus 5 into 10 power minus 3 divided by 5 into 10 power minus 2. So therefore, lambda is 5 6 is 30, so 0.6 into 10 power minus 3 minus 3, so this is 10 power minus 6. So this is 6 into 10 power minus 7, or I can write it as 600 into 10 power minus 9 meter. So therefore, the wavelength is 600 nanometer. So option B is the correct answer. Then question number 18, it is told, for sustained interference fringes in double slit experiment. For sustained interference fringes in double slit experiment, the essential condition is the sources must be coherent. Yes, the intensity of the two sources must be equal. So here only option 1 is correct. Means if the sources are coherent, it means their phase difference is independent of time. If their phase difference is independent of the time, then only the fringes will be sustained, and only the interference fringes will be sustained. Interference fringes are sustained. Interference fringes will be sustained. Therefore, only one. So option B is the correct answer. Then in question number 19, it is told, in single slit experiment, the width of the slit is reduced. Width of the slit. So we know that sine theta is equal to lambda by a for the first minima on the screen, for the first minima on the screen for the single slit experiment. So where A is the width of the slit. So if the width of the slit is reduced, then the linear width of the principal maxima. So the width of the principal, so if this theta is very small, then theta is approximately equal to lambda by A. And so here this is theta where the first minima is formed. So the width of the angular width of the central maxima, angular width of the principal maxima, angular width of the principal maxima, that is equal to 2 theta, which is approximately 2 lambda by A. And the linear width, that will be equal to this d into theta, I can say. So the linear width is approximately, linear width of the principal maxima, that is approximately 2 lambda by A into d. So when the width of the slits A is reduced and 2 lambda and this d, they are constants, so slit width is reduced, then the linear width of the principal maxima, let us call it as W, or I can say it as delta y, suppose. So the linear width of the principal maxima, that is delta y, this delta y will increase. So it will increase, so this width will increase, but its intensity will decrease. Since intensity is equal to the power by area. So when area, since the power is constant, when the area of the central maxima, that will increase, so the intensity has to decrease. So the linear width increases but becomes less bright. So option A is the correct answer. So hope you have understood all the first 19 questions on wave optics. So here we shall end the first part of this video on the previous year KCET questions on the chapter wave optics. So any doubts if you have, then please write us in the comments section. And please install our Sapience education application, since we shall upload some important questions on KCET exam on every chapter in the Sapience education application. So thank you everyone. Bye.